All right, everybody, we're getting down to the last of the content that's required for this course, so that's kind of nice. And maybe a few more videos and that'll wrap us up. So this topic is correlation, regression, and the line of best fit. So it's actually kind of 3 sections in one, and I'm sure you'll see that in your homework, but they all tie together so nicely that I'm just going to do them all together, and then we'll separate them out as we go. And if we need sample problems or something like that, I can do sample problems for each section as well. So let's start with correlation. What is correlation? So if two things are correlated to one another, in my head I hear you talking about this word relation. Okay, they have a relationship, and this co-bit right here means together, right? Okay, so basically what happens is we're looking for how closely are two things related. That's what we want to know. And it could be more than 2 things, but because of the co, we're just going to say 2. So how closely are 2 things related? And that's how do they correlate, right? That's what we mean. So basically, there's 2 ways that this can go. You can either have a positive correlation, or you can have a negative correlation. Okay, so let me give you some examples. Okay, think about this. If the temperature outside goes up, temperature outside goes up, what do you think happens to ice cream sales? Okay, and in my head I hear you saying, well, those go up too. And if we were in class, I would do the thumbs up, thumbs down thing. So as the temperature outside goes up, the ice cream sales also normally go up, right? Okay, it doesn't mean that we don't sell any ice cream whenever it's cold outside, but I can tell you in Texas in July when it's 105 degrees that the temperature is definitely up, and the ice cream sales are probably also up as well. Okay, so this is a positive. Maybe think slope of a line or something like that. This is a positive and this is a positive. And what I tell people is, you know, it's a positive correlation when they're both going in the same direction. Okay, so as the outside temperature goes up, the ice cream goes up. So you can even think of these as independent and dependent variables. Let's think for just a second. Which of these do we have no control over whatsoever? The ice cream, or I'm sorry, the temperature outside, right? That is totally independent. We cannot do anything about that. However, the ice cream cells, what those are, totally depends, or at least partially depends, on what the temperature is, right? So here would be my independent variable, and here would be my dependent variable. And if you were thinking along the lines of, say, an algebra course, which most of you have seen, okay, my independent variable here normally, again, goes on the bottom, right? Temperature outside. And the ice cream cells would be the dependent variable, and it would go up like this. And we'd probably have some data points, right? Like Brahms sold this much, and Dairy Queen sold this much, and maybe we had some extra sales at Sonic for some kind of shakes or something like that. There might be a whole bunch of data points, okay? But in general, what we think is when the temperature is low, when it's cold outside, ice cream sales are also low. But when the temperature gets high, like say out here is 100, then the ice cream sales, the dollar amount, also goes up. Okay? So as this one goes up, this one goes up. And that's why I said think about slope of a line, because rise over run, right? So rise and run are both positive here. So the slope of this, if we made a line out of that, and basically I can guesstimate a line that kind of estimates all of those, okay, it would look something like that. That's going to be called the line of best fit, by the way. So, and there's lots of techniques for how we average those, the distance from the line, and so on and so forth. But, and we'll deal with that. But the way that this looks is if this was a line of data, that's a positive slope. So that's why I said think about your algebra and your slope and positive, okay? Now the other thing though is a negative correlation. So let's think about that, okay? Oh, let me give you another look at this. What about if the temperature goes down? If I'm going this direction, what would we think about the ice cream cells? The temperature goes down, the ice cream cells goes down, right? So if the temp goes down and the ice cream cells go down, let me give you my thumbs up, thumbs down. That's a down and a down. Temperature goes down, the ice cream cells go down. Now you might think, well, those are negatives, and that's right, that's a negative. But when you think about slope, remember it's the rise over the run, that would be a negative divided by a negative, and what's a negative over a negative? Positive, okay? So what I tell my students in face-to-face classes, I wish y'all were face-to-face with me, is that if they're going in the same direction, okay, then your line will end up looking like this. No matter what we're doing here, the line looks like this as long as our temperatures are in the right order, 0 to 100, 0 to however many dollars that is, that kind of thing. So if they're both going up, it's a positive. If they're both going down, it's a positive. So if they're matching, basically, think about it kind of like that. Then I have a positive correlation. Let me grab this guy. Then I have a positive correlation when that happens. Okay, so then thinking about that and maybe putting all that together and thinking about what you know about lines and slopes and stuff like that, what do you think about negatives? Well, if up and up is positive and down is positive, then what? They can't go in the same direction, right? Because those are both positives. So if one goes up and the other one goes down, then they're opposite signs, right? A positive and a negative. When you divide those, rise over run, slope, whatever you want to think about there. Positive divided by negative, one's positive, one's negative. It doesn't matter which one's on top or which one's on bottom. Well, that means it's negative, right? Okay, positive divided by negative is a negative. So let's think about this. Here's an example. As my TV watching goes up, my grade on my exam does what? The more hours that I sit in front of that television, not studying, what do you think happens to my grade? Okay, it's probably going down, right? So if I go through and I survey all of the students in my stats class and I say, how many hours did you spend watching TV this last week? And what's your test grade? The more hours somebody watched on TV, then probably the lower their test grade's going to be, okay? Now, that's not always true. Some students are really good and don't have to study as much and that kind of stuff, and they can still make good grades, and we know that. But in general, what we would say is as one goes up, the other one goes down in this situation, okay? So note the opposite directions, right? So this one was same directions. These are opposite directions. Okay, that gives me the negative. Okay, that's how I get the negative here. All right, let me give you another example. How about this? If your amount of sleep goes up, then what about the amount of time on task for your class, doing homework or whatever? What do we think about that one? Well, that might be iffy, right? We don't know, okay? Some people, if they get more sleep, they might be able to spend more time on task. But some people, if they get more sleep, that might take time away from when they have to do any of their studies. So we don't know. That's a question mark. Okay, there could be no correlation. It could be a positive. It could be a negative. We don't know. What about this one? If my amount of sleep goes down, what about my attention span? how long I can study, pay attention, focus on something. What do you think about that? Amount of sleep goes down. Do I have more attention or less attention? And in my head, hopefully I'm hearing you say there's less, right? Well, what about that? Those are both negatives. So is that a negative correlation? No, that's a positive correlation, right? They're both going in the same direction. What about this? As the temperature outside goes up, what about your grade in stats? What about that? Well, if it happened to be a summer semester and it was that 105 degrees outside, a couple of things could happen, right? Your grade could go up because maybe you're like, it's too hot outside, I might as well study my stats, okay? So it could go up. But what about if you say, oh, the temperature outside's a lovely 95 degrees and it's perfect for going to the lake and I want to go out and float in my inner tube or ski or kneeboard or whatever you're doing, what would happen to your grade in stats then? Yeah, it might go down, right? That's what I heard you say in my head. Okay, so we don't know, okay, and maybe it doesn't have any correlation at all. Maybe they're not related at all. So we just don't know what's going on, okay? So that's a question mark again. We don't know. We'd have to see some data points and see what's going on. If we have something where we can look at this and say, oh, it's definitely a positive upward trend, then we would say, oh, it's a positive correlation. Oh, I didn't give you a graph for this one. But if we had a negative correlation, let me put it over here. I'm sorry. Okay. If we had a negative correlation, then we might say, oh, we looked at those data points and it actually had a negative effect on people's grades as the temperature went up outside because they all went out to the lake. Okay. So and one of our negatives was TV watching, number of hours, right? As that went up, my grade on the exam went down. Okay. So this would look like this. Susie Q doesn't hardly watch any TV at all, and she makes 100 on the test. Okay, but I've got some other people that are like this, and then I've got Joey way out here, and he watches a ton of TV, and he just bombs that exam. Okay, when I go to do the line of best fit, and I try to fit a line through the middle of this, I would see a definite downward trend, right? Or a negative slope to that line, if you wanted to think about it that way. And it would have to stop here, right? Because I can't do negative hours of watching TV, so it wouldn't be back there, but I don't have an eraser. Okay, so that's a definite negative slope or a negative trend, a downward trend here as far as my TV watching gets really high, my grade might really stink here. Okay, so it's going down. So that would be the negative guy right here, where you're in opposite directions. And again, it doesn't matter if the top is positive and the bottom is negative, or if the top is negative and the bottom is direction. It doesn't matter at all. If you've got a thumbs up and a thumbs down, those are opposite directions, you're done. That's a negative correlation. Okay. So what about some of these question marks? That's what people start asking. Well, there's a couple of other options. Okay, these were both linear. There's a no correlation. Okay, and what that means is we just can't find a trend. We just can't estimate it. Okay, we can't find a trend. We don't see a line of best fit anywhere. Sort of like no pattern. There's no pattern at all to that data. We can't see anything. Okay, so that's one of the things that could happen. Oh, sorry, let me scoot that up. Okay, and one of those examples might be as the temperature goes up, what happens to your test grade? Okay, temperature up, test grade. Well, we don't know, but there may not be any correlation at all. Maybe it affects one or two students, but overall the rest of the students all do just about the same as they did when it was cold outside. They may not care at all that it's warmer out. Okay. And then the other option that happens a lot is maybe it's nonlinear. Okay. So linear means line, right? So the data forms a trend, but it's not a line, not a straight line. Okay, so that's something that could happen. So, and I'm just going to give you an estimate of that. And whenever I do these graphs like this with the dots on them, like that, that is called a scatter plot. Okay, scatter plot. Literally because we're just taking data points and they're scattered around, and so there's not necessarily a line or something like that. So it's called a scatter plot. And by the way, you can make your calculator do those if you don't know that. So for instance, here could be the years of hunting that we do, and over here could be the deer population. Okay. So sometimes if the deer population is really high, they'll be like, oh, let's do more hunting and whatever. And suddenly the more we hunt, the lower the population gets. And that could actually be a bad thing, right? You might have some years that are here or here, some that are not quite on trend with the rest of them, but that's okay. They might be outliers. We have that word. We know that word. Or they might just be a little bit farther away from the line of best fit. In this case, it wouldn't be a line of best fit. What's that? In that case, it would be a curve of best fit. Okay. So normally, and especially in this class, we're not going to deal with those curves, right? Whereas this one up here was a line of best fit. Okay, we're not going to deal so much with those curves. If you want to see it, I can show you how to make your calculator find those. But this is more of an exponential decay kind of a graph, and that's what normally happens with population, is it's an exponential equation, and we're not dealing with those in this class. But if you were in my college algebra class or something like that, we might do some of those. So that's what's happening there. But in that case, it's not a linear, right? That's not a straight line. That is a curve. Okay? All right. So in general, think correlation, positive, negative, or no correlation. Or we could have some weird nonlinear stuff that you could have a parabola or something like that. And I'm going to show you some graphs and we'll talk about them. It's important to remember that correlation is not causation. Okay, so that's an interesting point that you'll see in some of your reading. Correlation is not causation. Okay, so what does that mean? It means it doesn't cause something to happen. So just because the temperature goes up outside, it doesn't mean that the temperature is making people buy more ice cream. Okay. It could be a contributing factor, and if you're like me, you could go, oh, the temperature is warm, I want ice cream. So it might make me think that I need ice cream or want ice cream or whatever, but it doesn't mean that the temperature is forcing me, it's causing me to have, to eat ice cream. Okay, so just because you see a relationship, in statistics in particular, you got to avoid that word cause. It doesn't mean it causes it. The reaction. So it takes a lot actually in statistics before somebody will go, oh, it causes that reaction. One of the few things that I would say that statisticians can agree on is that for one of the things that I've seen some data on that is like pretty close to 100% is lung cancer. So what do you think something that causes lung cancer? Well, it could be asbestos, breathing in asbestos, could be radon, stuff like that. But one of the leading, quote, causes of lung cancer is smoking, right? And so that it takes a lot for somebody to put, for a statistician in particular, to put that word causes in there. And so there's got to be a lot of data on that. Now, that doesn't mean Joe Schmo on the street needs a lot to use the word cause, but statistically speaking, what has to happen is we have to have something that's statistically significant, like very statistically significant. And we'll talk about that statistical significance later when we look at our confidence intervals and stuff. So that's one of the last topics of the class. But yeah, it doesn't mean it causes it. So steer clear of that word causes. We know that that's not necessarily the case. So watch out for that. And here's the thing about it. What we need to keep in mind is if we can find a strong correlation, okay, between two variables, okay, then we feel closer to being able to find a cause. We feel closer to having a cause for some outcome. Okay, and basically what I'm saying about smoking is that there's such a close relationship between smoking and lung cancer that pretty much most people, especially doctors and scientists, would agree that there is causation there. But it's because there's such a strong correlation between them, okay? That's what's going on there. So let me give you some pictures so you can see what the heck she's talking about. And I'm just going to throw some pages out of a book up here because that's probably way better than something that I would put together. All right, so look at these. Okay, these three right here. This is kind of just a scatter plot, and there's a lot of points all over the place. But if you look really closely, we've got some points kind of down here in the bottom left, and this kind of rises a little bit right here. And if you look here, same thing, kind of bottom, and then it kind of rises. And overall, I can kind of see right through here in the center, maybe we've got what would be a line of best fit. Now, here's the problem. Those dots are really, really scattered, right? They're not really close at all, okay? But they kind of look like they're going up. So I would say probably that's a positive relationship. The book actually says, now R is the variable for correlation coefficient. So the book says that their R value is 0.3. Okay, so what does that mean? An R value of 0.3 means that about, make this into a percentage, 30% of the outcome, okay, whatever this Y variable is here, the unknown, the dependent, about 30% of those outcomes can be related back to maybe they were caused by the independent variable, okay? So now look at this one. Okay, that's definitely an upward trend, right? Okay, starting down here, going up here, down here, up there. Overall, we started out low and we went up high. And these are much closer together. They're clustered more or grouped more. And your book says that their correlation coefficient is around 0.7. Again, make that into a percentage, 70%. So it's about 70% of whatever my outcome is here can be related back to the original, whatever the input is, whatever the independent variable is, okay? And then over here, look at this straight line, all these data points. Straight in a line. Okay, they say R equals 1. Now think about that. If that was a percentage, that would be 100%, right? Think about the probabilities and stuff. The highest you can go is a 1, right? So this would be 100%. So these are all, this only happens, 100% only happens when they're all in a very straight line like this. So what that means is that 100% of the outcomes, R equals 1, 100% can be related back to whatever your input was here, okay? And notice that these are all positive, and that's because we've got this positive direction going here. Look at the other three. Notice this one's really spread out, but again, it's kind of starts up a little bit and goes down here. So look at the overall general direction of the stuff. It's kind of negative, right? Okay, so look, they've got a negative 0.3. So that's about negative 30%. Now all that negative says is that as one goes up, the other goes down. Okay, so this has an inverse relationship or an opposite direction. Okay, this one, negative, definitely we have a downward trend here. Okay, but definitely these dots are closer together than those dots were, right? And so we would say this is more closely correlated to each other. Okay. So I want you to think correlated whenever you see correlated. Okay, you'll hear me say that sometimes. Okay, so those are definitely closer tied together here than these were over here. Okay, so they've got a 0.7. It's about 70%. But notice the negative out in front. That means that they're in a downward trend. And then the last one here is the negative 1. Again, the 1 just means 100%. They are in a straight line, baby. They absolutely have a straight line. It is very easy for me to put the line of best fit just right on top of that. It's going to hit every single data point, right? Over here, if I put a line of best fit on top, I might hit some of the data points, but I'm not going to hit them all. Okay, but here I would hit every single data point if I put a line on top of that. So it's a 100%, but it's negative because it's a downward trend. Okay, so that's kind of the difference between a correlation strength. When it's weak, these over here are considered weak. When it's a moderate, okay, they're calling it strong. And this would be if it was perfect. Okay, so then we have the other two situations I mentioned. These are just scattered. You don't see any plan at all. There's no pattern in there. Okay, so right here they say it's no correlation between the x and the y values, and so the r equals 0. So that's right in the middle. It's not positive, it's not negative. We don't see anything going on here, and that might be, I don't know, it's getting hotter outside. What's going on with your stats class grade? I don't know. And then the last one, this is clearly not a line, right? So nonlinear. I gave you an example of that. Okay. So you're going to look at that and you're going to say, oh, I understand when it's positive, when it's negative, when the correlation is 0, there's no pattern, okay, and so on and so forth. So let me give you some examples and we'll talk about it. Okay. Look at this one right here, 27. This is from an old test. Okay, I've got some scattered points. Is that a positive or a negative direction? In my mind, I hear you say positive. And then what about this line here? Okay, it's a linear pattern, okay, and it's positive. And they gave me here some options, 95%, 65%, 20%, or a negative 65, okay. Well, we know it's not negative, so we can dump that one. And it's probably not 20% because that would be a little more scattered out, right? So it probably gets between the 0.95 and the 0.65. Now 0.95, that's really close to 1, right? Do these look like they're exactly in a straight line or really close to it? I don't think so. Okay, so they're kind of scattered about. Some one's on one side, one's on the other. So the 0.65 is what I would look at for that. So it's not perfect, it's not close to perfect, but it's really not spread out like these. But then look at this one. What about these? These aren't perfect, so it's not a perfect one. But it is a positive correlation, and think about what's going on there. They're really, really close, right? So they're saying their options here are negative 0.9, positive 0.9, 0.5, negative 0.5. So I would think that it's positive 0.9. They're really, really close. Close to 100%. Okay. That's a lot, and that's a lot closer. The 0.9 is a lot closer than the 0.65, right? Okay, so this one right here. We've got a scatter plot. It generally looks like it's in a positive upward direction. But then we have this one point out here. What do we think about him? We think, hopefully, maybe he's an outlier. Okay? Maybe he's an outlier. Maybe he doesn't fit with the rest of this data. Now, we can't just say he's an outlier and dump his grade, right? We have to actually do the analysis that we figured out on the last test or two and figure out, can I dump that or can I not dump that? But in general, he looks like he's an outlier because he's not in the straight line here. If I was to draw the line of best fit here, I'd go right through the middle, right? Okay, so that's the way that would do. The process of finding the line of best fit, and I'm going to skip that one down there. The process of finding the line of best fit is called regression. Okay. And by the way, let me get that out. The process of finding the line of best fit is called regression. Okay. And like I said, by the way, I can do this on my calculator. You're not going to have to do it on the calculator for this exam. If you do, I'll tell you about it. I'll make a separate video with calculator work and stuff like that. But you'll have to be able to see correlation. You'll have to know if it's positive or negative, how closely related, and so on and so forth. So the process of finding that line of best fit is called correlation, or I'm sorry, called regression. And I can do lots of types of correlation. I'm sorry, regression. I've been saying correlation too much now. Okay, so for instance, we have linear regression, which is the one we're going to do for sure in this class that you will be responsible for. But there's also quadratic regression. Okay, what the heck does that mean? That means that, and there's lots of different kinds. There's that exponential and so on and so forth. That means that if I looked at a graph and I saw my data points looked like this, and I see a pattern in there, and I want to find a curve of best fit, then I'm going to look at this and I go, oh, I think that that's a parabola, right? And if that's the case, then that's quadratic regression. Okay, to be able to find the equation for that graph. Okay, so if I have points that are doing that, I'm not going to turn around and try to do linear regression on that. It doesn't make sense because I know that all my points are not in a straight line, right? I would only do linear regression if I thought that they were all in a straight line. This is not, so I'm not going to do that here. So now I'm going to be like, oh, what do I do about it? Okay, we do quadratic regression. For anything like that, you would use a graphing calculator. So whenever I show you how to use the graphing calculator for linear regression here in a little bit, just know that your graphing calculator will also do those. Okay, these are all going to be straight lines that we can approximate a line of best fit. And they're called linear regression, right? Okay. We can also do that on our graphing calculator. However, I will say there's some kind of extreme math in the book. Let me show you some stuff. This is the not too bad one. This is one way to find the correlation coefficient. Okay, let me show you this equation. So if you look at that, look at the top of that, x minus x bar, well, that's the data point minus the mean. Divide by s sub x. That's the standard deviation on the x values. Okay, that's what that sub x means. Y minus y bar, okay, that's your y value minus the average on the y values. Okay, divide by s sub y. So this is immediately more complicated than, say, standard deviation or something like that because I have two variables. When we did standard deviation in the class before, and when we did finding all of our different stuff like that, z-scores and things like that, we were only dealing with x values, right? So that was one variable. But now, because we're going into a grid, basically, a Cartesian coordinate system where I have both x and y, when I do those calculations, I would have to account for an x standard deviation and a y standard deviation. So the y value minus the average on the y, so that would be the mean on the y, divided by standard deviation. You would sum all that stuff up and then divide by n minus 1. That gives you your r value. That's one of the easier of the things you could do here. Let me show you this one. This one's just really nasty. Okay. Number of data points times the summation of your x times your y minus the summation of all the x's times the summation of all the y's divided by square root, blah, blah, blah. I'm not even getting into all that. Whenever I show this in my face-to-face class, I'll tell them, do y'all want to do that by hand? Or I'll ask them, do y'all want to do that by hand? And they almost always go, no, because we remember how much work just doing standard deviation was on, say, 5 data points, 6 data points. We certainly don't want to do 20 data points and have to find this R correlation coefficient, right? So for an exam, you would use your graphing calculator, okay? You would use a graphing calculator. You would, or you would need to just know the difference between R values. What's a high R correlation coefficient mean, and so on and so forth. So let me throw that out here. I've mentioned it a couple of times, but I want to get it in print. Correlation coefficients tell you the strength of the relationship you are examining. Okay, examining. Okay, where the variable used is R. Okay. Where R equals 0 means there is no correlation. R equals 1 means there's a perfect correlation. And R values between 0 and 1 are somewhere in between. Okay, so that should kind of go with what we said whenever we were looking at those graphs, right? Okay, somewhere in between. So what does the value mean? R lets us know approximately, what portion of the outcome can be accounted for by looking at the independent variable. Independent variable. Okay, so what does that mean? Well, if it's a 0.3, then that's about 30% of the outcome can be accounted for by whatever the independent variable was there. Okay, so if your attention span is down and it's a 0.7, okay, that's related to how much sleep you got, okay, then lower sleep means lower attention span. Then that's about 70% of your attention span deficit can be related back to, can be seen as accounted for by the fact that you didn't get any sleep last night. Okay, that's what that means. Okay. In addition, let's stick this in here. Also, R will be positive or negative depending on whether the correlation is positive or negative. So you'll stick a sign out there, positive or negative, plus or minus. Okay, so that basically sums up all the stuff I just said about those correlation coefficients. Plus the fact that the equation for these is terrible, and we don't want to do that. Okay, we absolutely do not want to have to do those calculations by hand. So we want to make sure everybody knows that. Okay, so moving on. You might see some examples where they talk about correlation, and you have to identify whether you think it's a big correlation or not a big correlation, and so on and so forth. You have to keep in mind the fact that sometimes the correlation you see, it might just be a coincidence. Okay, so there could be other things at play. You could have confounding variables that are messing with your results and stuff like that. There could be some underlying cause that we don't see, that we didn't account for in our study. So there are sometimes other things that might be going on. Even though I got a positive correlation between temperature and ice cream cells, maybe, I don't know, maybe the ice cream store put it on sale that day. Okay, I don't know, maybe ice cream is on sale. 2 for 1. Okay, I don't know about y'all, but whenever I see a good deal, 2 for 1, I'm more likely to purchase it. Okay, yeah, so think about that. What about this? So there could be confounding variables. Remember those from the beginning of the semester. Or underlying causes. Things that we don't have in mind. How about this one? What happens when the temperature goes up outside? It's always outside for me. Okay. But, I mean, we could talk about an inside temperature. Like, if it gets really hot in the classroom, how likely are you to pay attention to Dr. Webster? Not very likely, because the warmer it gets, the more likely you are to, like, go to sleep or be panting or waving your fan in front of your face or whatever. Okay, so you could talk about inside, but I'm talking about outside temperature. As the outside temperature goes up, what happens to hot chocolate cells? What do you think about that? Okay, if I go to, say, Six Flags and I want hot chocolate in the middle of the summer, what are they going to tell me? They're probably going to say, "Lady, are you crazy? We're not selling hot chocolate, we're selling ices." Okay, Six Flags not selling hot chocolate in July in Texas. Okay, so probably the sales of hot chocolate go down when it's hot outside, right? Not a lot of people want to drink hot beverages. This is not true for, say, your morning coffee. If you're a coffee drinker and you drink coffee every single morning, it doesn't matter. Now, some people might switch to iced coffee or something like that, but coffee sales in general, Starbucks is probably not in trouble, even if it's summertime in Texas. All right, so what about that? One's up, one's down. Negative correlation. But can we say that the drop in the rise in the temperature, sorry about that, that the rise in the temperature causes the hot chocolate cells to go down? No, not really. You know, some people might want to buy hot chocolate and have it on hand. I don't know. So things happen. Okay. What else? One more little thing about these lines of best fit and stuff like that. Well, I guess two things. Let me pull back what I had earlier. Let me grab it. Where are you? Okay. So one more thing. Or two actually, but if the line of best fit is a really good line of best fit, if the outcome can be mostly related back to whatever the independent variable was, then sometimes we can use these lines of best fits to make predictions. Okay, so let's think about that. This was temperatures and ice cream cells. So if June 15th we're right here and it's supposed to be even hotter tomorrow, if today was June 15th and it's supposed to be hotter tomorrow, then we might use our line of best fit that we came up with to determine where can I put this for tomorrow? What about the day after? What about the day after? So we might be able to forecast what's coming up or make predictions, okay, if we have a really good model. In line of best fit, we may be able to use the line of best fit to make a prediction. Okay, especially if the prediction is short term. Okay, if we have a really good model and I want to, it's June and I want to know what do I think is going to happen in July of the same year, probably I can use that model to make that prediction. Okay, if the model is so-so, then it might not be as good of a prediction. Or if my time is really long, so what if I want to predict it for 3 years from now, what's going to happen in July, let's say July 4th or whatever, then maybe my model's not as good long term. So we have to think about that and look at those things happening and watch out for it. Okay. And I think the last thing I want to tell you about this is that as we find some different stuff, if we use our graphing calculators or whatever, there is another variable or another use for R is to find R squared. Okay. Which is an estimate of the variance in your data points. Okay, so what that means is, say that, and I'll use a nice easy one, say that if R is 0.3, okay, then R squared is what? 0.3 squared, which would be, take your 0.3, multiply it. 3 times 3 is 9, but I've got 2 decimal places, so I would put a 0.09. You can put that on the calculator if you want to. Okay, 0.09. Okay, so make sure I did that right. I'm sorry. My brain is just not working right now. Yes, I did well. Okay, so if I get that, then this will talk to me about the variance between my data points. So how much of that can be accounted for using whatever model that we're using. So that is out there. We've used the word variation before, variation, whenever we were talking about range and stuff like that, how much variance or variation is there in my data points. We talked about sometimes your data points are really clustered together, really close and tight, and sometimes they're spread out more and that kind of stuff. So this would be my relationship for how that happens, okay? How I know if my variation is big or not. So if it was a 0.3 for my correlation coefficient, for instance, and then I square it and I get a 0.09, then how much variation do you think that represents? There's a little bit, but not a ton, right? Okay, so this is kind of mild. So if I had a lot of variation represented by this thing, so what this tells me is that I don't really have, whatever it is that you're thinking is the causing variable, the one that's the independent variable, not causing, I'm sorry. So whatever it is you think is the independent variable, it's not really having that much of an effect on what's happening between all your data points, okay? It's not causing a lot of the variation. There's something else that's probably causing a lot of the variation or representing the variation. It's not whatever my independent variable was here, okay? So that's where variance comes in, and that's how it's related to correlation. It's just the square of whatever I was already looking for. So that's about it. I'm going to throw this out here. There is a little thing in one of the books that I use that talks about the Supreme Court Justice Ruth Bader Ginsburg. And here's what she says. Proof beyond a reasonable doubt is proof that leaves you firmly convinced of the defendant's guilt. So proof beyond a reasonable doubt. There are very few things in the world that we can know with absolute certainty. And in criminal cases, the law does not require proof that overcomes every possible doubt. Okay? So we're not talking absolute certainty. Okay? That would be causality, more of causality. Okay? So what we are talking about is proof beyond a reasonable doubt. So what she says is, if, based on your consideration of the evidence, you are firmly convinced that the defendant is guilty of the crime charged, then you must find him guilty. If, on the other hand, you think there is a very real possibility that he is not guilty, you must give him the benefit of the doubt and find him not guilty. So that's kind of an interesting thing. Possible cause, maybe it's related. Probable cause, oh, that's a lot more strenuous. And what she's saying is cause beyond reasonable doubt. You've got some kind of a physical model that is so successful in explaining what's going on, what's causing another, that there is absolutely no reason to doubt the causality. So that's what's going on with, for instance, and I'm going to go back to the one that I can say for sure people agree on is smoking. That for sure people agree that if you smoke, especially long term and heavily and that kind of thing over years, whatever, that it will, quote, cause lung cancer. So please don't smoke. That's kind of my public safety announcement on the side. But that is one of the very few things that you will find throughout the literature that they will say, oh yeah, that's cause, not just correlated. Okay, so that's kind of an interesting point to leave us on. That wraps up correlation and regression and line of best fit. I will make a separate video about how to use your calculator to find regression, line of best fit, and to actually find the correlation coefficients without having to do all that by hand. So I will post that as soon as possible. Thanks. If you have questions, let me know.